Welcome to the Dayton Superior Learning Center. This session, we will discuss the use and application of the design of concrete form pressure. This presentation is protected by U.S. and international copyright laws. Any questions or regarding to technical specifications, please consult www.daytonsuperior.com or consult the Dayton Superior Engineering Group. We are going to talk about concrete form pressure. Concrete, typically when it's placed, it is a liquid and therefore puts out a pressure onto the form. And that form is typically exerted in an equation of P equals WH, where pressure is the pounds per square foot, the weight of the concrete, fresh placed concrete, times the height of the concrete pour. So concrete typically puts out a pressure of about 150 pounds per cubic foot in each direction. So that means it's going to exert 150 pounds per square foot in each direction. Basically, when it's plastic, it'll take the shape of the forms. The forms are basically the mold of what you're looking to make the concrete into. So it will bear sideways against the form with a pressure of 150 pounds per square foot. Doesn't matter how wide the walls are. 1 square foot of concrete pressure is still 1 square foot of concrete pressure. Doesn't matter if you only have a foot in there at 30 inches wide or at 12 inches wide. You are still only going to exert 150 pounds of pressure outward on the concrete forms. What does vary the pressure is the rate of pour on how much concrete you're actually putting in the concrete form. So basically what they call a rate of pour is the vertical rise of plastic concrete in the forms, expressed in feet per hour. How many foot of concrete are you putting in the form in 1 hour's time will give you what kind of pressure you're going to put on the concrete form. Now, when you're putting concrete pressure or concrete in the form, you're filling it up. Concrete is incremental. It will actually add to itself. So what happens is, if you take the wall here at 10 foot tall, eight foot high, sorry about that, 8 foot high wall, and you pour at 8 foot per hour, you will exert 150 pounds on the top foot of that concrete form. But on the bottom of that concrete form, you're actually going to be placing 1,200 pounds per square foot on that form. Depending on what the load rating is of that form, you more than likely overloaded it and will have issues with it. As concrete sets up, the pressure on the forms disappears. Now, basically, remember we said concrete form rate per hour. How many feet do you put in the form in 1 hour? So if you were to put 5 foot of concrete in a form, you would develop 750 pounds per square foot down at the bottom of the form. After that first hour, that 750 pounds is no more because the concrete has started to set up. So once the second foot actually starts to set up, which is, let's say it's 15 minutes or 10 minutes, 12 minutes to take you to pour each foot, at 1 hour, the 750 pounds is what 12 minutes later, the 600 pounds per square foot is now null, because what happens is the concrete is set up enough that it is not exerting the pressure on the concrete form. Temperature does play a factor in all this. All these numbers here are basically off of 70 degrees temperature in Fahrenheit. But typically, if you're talking, if it's colder, it's going to be a little bit longer for the concrete to set up versus if it's a little bit warmer, it's going to set up a little bit faster. So given the concrete temperature, the faster the pour, the greater the form pressure. So basically at 1 hour, if you pour in 5 foot per hour, you got 750 pounds. If you only pour a 3 foot an hour, you only got 450 pounds per square foot. Typically what you're looking at is if you're going to pour an 8 foot high wall, it'll take you 2 lifts of 4 foot each for a total of 2 hours to place that wall properly at a pour rate of roughly 4 foot per hour. Many contractors base their pour rate on an assumed concrete temperature of 50 degrees for winter work and for 70 degrees in summer work. This gives them a little bit of leeway because typically most contractors don't like to pour concrete below 45 degrees in the winter months. So usually they're pouring concrete, it's a little bit warmer. And in the summertime, at 70 degrees, you typically are, that's, even if it's 75 or 80 degrees, the concrete is going to set up a little bit faster on you, which could be a separate problem all in itself. But typically, as far as form pressure goes, you will not be exerting the full maximum load of concrete pressure on that form. So pressure, liquid head, when you put pouring concrete, you've got a pressure at 4 foot of 600 pounds per square foot. At 6 foot, you're about 900 pounds per square foot. At 8 foot, you got 1,200 pounds per square foot. At 10 foot high, you're at 1,500 pounds per square foot. Now, plywood typically will let you exert 600 pounds per square foot. So that'll enable you to pour concrete at roughly 4 foot an hour using plywood forms. That's using plywood with any of the backing material, whether you've got 2x4 studs and wales, whatever spacings to accommodate it. But what will happen if you pour that concrete any faster is you will get a pillowing effect in the concrete form. Steel ply, for example, which is a modular forming system, steel ply typically will allow you to pour up to 1,000 pounds per square foot. So working backwards at 150 pounds per cubic foot to get that 1,000 PSF, we can come up with 6.67 feet or 6 foot 8 inches of concrete can be poured in an hour using a modular forming systems. Hence, one of the advantages of going from plywood forming to a modular forming system. Remember that the wall thickness does not affect the concrete form pressure. The height of the concrete pour does affect the concrete pressure. Concrete typically comes in various densities. You can, in today's marketplace, you can get concrete that is what they call lightweight concrete, which is only 130 pounds per cubic foot. You can get a high density concrete, which is 180 pounds per cubic foot. ACI typically recognizes that these concretes are in the marketplace and are being used. The way they look at it is if you're using 150 pounds per cubic foot, you are in the range of being in the safe working load of that product. Concrete characteristics. Wet concrete acts like a liquid. It's in a fluid state, so it will flow. As concrete sets, pressure is reduced. So obviously, as we showed you earlier in the slide, after an hour that you're going to that bottom foot of concrete, typically once you get to that 1 hour, is null and void. And then every 12 or whatever, however long it took you to pour the next foot, once you get to that level, 1 hour after you started pouring that, it is cured and the pressure is then reduced. The only one that can control this is the contractor. We can tell the contractor all day long how fast to pour his concrete. But once he gets out on the job site, the contractor is the only one that can control it. Concrete is typically strong in compression and weak in tension. So typically, the compacted version of concrete is much stronger than a tension piece where concrete is stretched out over a large opening. Factors that will affect concrete setting time is slump, vibration, admixtures, and temperature. Let's talk first about slump. Slump measures the consistency of the concrete, the flow, the workability, etc. The higher the slump, the wetter the mixture. So slump is measured in inches. Different slumps typically are used for different purposes. Typically a range of 2 to 4 inches is typically for 12 inches in height of concrete for a floor slab. Typically with a wall, you're typically going to be somewhere in the neighborhood of 3 to 5 inches of slump for a concrete wall. Remember, if you add 1 gallon of water per cubic yard of concrete mix, you're going to increase the slump by 1 inch. Always be the specified slump will not exceed 5 inches, for example. That is always the example that you want to have. Once you get above 5 inches, the material means it's going to really just flow. And it's going to take a little bit longer to cure out. And the one problem you do have is at that point, you may end up starting to get aggregate that's going to separate from the liquids in the concrete. A slump test, just so everybody knows what a slump test is. The slump test is where you're going to take the concrete, mix it in this, basically compact it in this, for better, slump cone test tube, and then flip the cone over and remove it. Once you remove it over, you basically take the slump cone, set it over to the side of it, put a flat level across the top of it, and measure how far down the concrete has settled to actually get the actual slump of the material. So typically, if you're looking at concrete and here's your slump cone that you've actually filled, you put it in place and then pulled the cone off, and this is what you end up with. You've got a 4-inch slump. Typically, that is a good product for flat walls, for walls and for flat floors. May be a little bit thick for the flat floor because I know most guys like to use a flat slump of about 5 for a floor slab. As you can see, here's the true accurate measure going on off to the side in the site. Vibration. typically every job has to have concrete has to be vibrated. There's a couple of different ways you can go about the vibration. You can do an internal vibrator, which basically is a vibrator with a head that actually you stick into the concrete. And what it is it's rotating or vibrating at a very high frequency. And what it's doing is it's pushing the air out of the concrete mix to the sides of the wall panels, and then the wall panels, that's enabling the air to travel upwards and out of the concrete. Typically, that is recommended for most concrete projects. A couple of things you do have to worry about internal vibration is on the concrete. If you take a vibrator head and stick it in concrete, especially concrete that is just set up or got its initial set, and you hit it with the vibrator, you re-liquefy it. So now all of a sudden, if you re-liquefy it, now you have to add that weight back into your equation for concrete form pressure. External vibration, only recommended on heavy duty steel forms like a precaster would use, primarily because the external vibration typically shakes the form system, sends a wave through the form system, creating a vibratory pulse. And what happens is this material then will it shakes the form, vibrates the concrete, removing the air off to the side and helping it escape up through the sides between the forms and the concrete. Revibration is where you have concrete that's already started to set up in this initial set, and you end up sticking the vibrator head into it, re-agitating it back into a full liquid head. So at that point, you need to start recalculating your load pressures based off of where you stopped revibrating, and based off of concrete height. Air entrainment does not affect the setting time. Accelerators speed the setting time, like calcium chloride is used a lot of times by masons to actually to speed up the concrete that they use to set their blocks and so forth. But contractors typically will use calcium chloride to help speed up things as far as the setting time. Retarders typically slow it down. The pozzolans, like fly ash, has a two-edged sword. Typically, it makes concrete much easier to work with, but it also has, and it also helps in abrasive resistance of material, but it also makes curing a little bit harder of the product. Low concrete temperatures basically slow the setting of concrete. Concrete, if you're in a low temperature situation, concrete is going to take longer to set up. Once again, this is the chemical reaction. So if it's a colder situation, it's going to take longer to set up. If it's a higher, it's going to speed it up. Primarily just because of the chemical reaction taking place here. It's going to be much easier to move along during that warmer weather. Air temperature does affect the concrete temperature. Now we use the formula P equals WH. That was the simplified formula because most contractors, like myself, typically find those much easier to use than the ACI formula, which here in a wall version typically will give you the maximum pressure to be considered, which is 2,000 pounds of concrete pressure per cubic foot. So what we're looking at here is with this formula, that's what you would use for walls. And they have a column that actually calculates 4 columns. The wall dimensions here, usually with the P equals WH, you're within 5%. And that is it for understanding concrete wall form pressure. If you have any questions, please feel free to get a hold of me at training@DaytonSuperior.com or give me a call at Chuck Hoke at DaytonSuperior.com. Thank you.